We are going through the practice test 2 for Organic 1 today. I'm Dr. Little at Florida State University. And so we're mostly going to be covering arrow pushing, resonance, and nucleophile, electrophile stuff, along with some acid base stuff. So we're going to start with arrow pushing. So arrow pushing, we're showing the movement of electrons. We're literally moving charged particles around. So usually when I think about arrow pushing, I find it helpful to focus first on the change in charge. And I think a lot of people don't necessarily want to think about that first. They want to imagine bonds moving, which are important, don't get me wrong. But when you look at the change in charge, you notice that from starting material to final product, we've gone electrons have ended up down here and have come away from down here, from up here, right? There's been a general change in charge, right? Everything was neutral here. In this situation, the negative charge is down here. So I know that the charge had to have gone this direction. I know electrons had to have traveled this direction along the chain to get this change in charge. There's a couple other ways you can think about it. You can think about alcohols being electron donors, right? So more likely than not, that's going to give electrons. Another dead giveaway is that if you look at the lone pairs on this oxygen, and then on the same oxygen on the final product, it's lost a lone pair. So one of those lone pairs had to go somewhere, and the closest place it could have gone, the only place that explains this product that it could go to is that bond. This carbon's got 4 bonds, so I can't just make another bond with it. So I've got to move this one over. We kind of continue the chain until we get to this end carbon. Another thing that's kind of weird about this that gets people off is people don't like to end a charge on a carbon for some reason. That carbon can hold a negative charge. Happens all the time. Um, this reaction, we it helps to understand and to start drawing out implied hydrogens in the area that changes, right? Notice that this is the area that changes from starting material to final product. And the first thing I notice is that this carbon goes from having 2 hydrogens to 1 hydrogen. So any sort of change that is shown in an arrow pushing question has to be explained by the arrows. You can draw totally reasonable arrows, like this arrow wouldn't be unreasonable, but it doesn't explain the product, right? So it's not what the question is asking for. The question is asking to explain the product, and one of the things that's different about the product is we're missing a hydrogen. So actually, I'll do it from this one so it's clearer. We're going to take one of these hydrogens, and we don't want this hydrogen attached to this molecule anymore. And the thing that's holding it to that molecule is this bond. So we're going to break the bond between the hydrogen and that carbon because we don't want the hydrogen attached to this molecule. And that's what forms our double bond. And that satisfies the positive charge by getting an electron through that double bond. I would say when you see a question like this, whenever you see a metal, draw out the ionic bond. Draw a whole new molecule with the ionic bond. We'll see that throughout this practice test. Just go ahead and do it. Lithium's a metal. This shows us kind of where the separation of charge is. And now we can start to get an idea, right? Again, if I look at the change in charge from starting material final product, I notice that this oxygen has gained electrons, right? So the only place it really could have gained electrons from is this double bond, which that should be a motion that we're pretty used to at this point. But that would make this carbon deficient in electrons, right? So more likely than not, that bond went up there. And we also have to explain how this carbon, right? We can imagine 1, 2, 3 being 1, 2, 3 attached to that carbon. So we've got to show an arrow showing the bond, right? Because arrows show formation of bonds. There needs to be an arrow between those two things because we know that they're bound together in the final product. We also know that the arrow has to flow in this direction because this is the side with the negative charge, right? So arrows are going to flow from things to negative charge to things with negative charge. So it makes sense that the negatively charged thing is the start of the arrows, and if we end the flow, it ends up here which is what ends up with a negative charge. Um, so this is kind of a little bit of a tricky question. So what it's actually doing is this. It's not that tricky. It's just showing it in a different form, right? Um, so in order to go from here to here, again, this is a reaction just like we just saw, where one of these carbons is losing a chlorine. It has one hydrogen, and the other one of the carbons is losing a hydrogen, right? Because there was two in the starting material and one in the final product. So a negatively charged hydrogen has a lone pair. It's going to take that hydrogen, and I've got to do something with that bond. I'm going to collapse that bond down here to form the double bond, but that chlorine is also gone. So the way a chlorine leaves is by taking its electrons and going, right? So you can imagine a Cl minus here. Uh, this is a very common theme, right? You see these kind of reactions all the time. It's called an elimination reaction. So I'd keep my eye out for it. It's a reaction that we're going to see throughout the rest of the semester. All right, again, things have changed all through here, right? This is a negatively charged thing and it ends neutral, so I know electrons are probably going to be flowing away from this oxygen. So my first guess is going to be something like that. That's my initial thought, right? That would make sense to why this becomes neutral, and it would explain the double bond here, right? So the first place I'm looking at is the charge. Uh, I also see that this is charged, the bromine's charged, so it's probably leaving, which tells me something's picking up this hydrogen. All right, this hydrogen is being taken by something. I look throughout the molecule, I see, hey, there's no hydrogens here, no hydrogens here. One hydrogen, one hydrogen, one hydrogen, two. There's two hydrogens here, right? That went from an sp2 to sp3 carbon. So something changed. So this carbon can't have more than four bonds, so I've got to move that bond. And then notice I've got this bond that has to go somewhere. And it doesn't just end on this carbon, because then the carbon would have a lone pair. What it ends on is this hydrogen. It explains the formation of the bond to that hydrogen. Um, this is a cyclization. So again, I'm going to look at the negative charge. That's probably where my arrows are going to start. I'm going to push from a negative charge thing. And notice I know that this oxygen in the final product is bound to the carbon connected to the nitrogen. So it makes sense that that oxygen would attack that carbon. That carbon already has four bonds. There's a hydrogen here, so I've got to break a bond. So I'm going to break that double bond and push it up to the nitrogen. Make sure all of your arrows are either starting from a lone pair or a double bond. Just double check yourself on that because you will lose points if you're not drawing things from lone pairs. Right? Even here, even on this carbon, I draw it from a lone pair. All right. So these questions are pretty similar. We're still interpreting arrows, but now one of the tricks is we have to understand the um, stereochemistry that we're creating with these arrows. So there's a set of rules where if something that's planar goes to something that's tetrahedral, we get wedge and dash. We form two products, both the wedge form and the dash form. Tetrahedral to tetrahedral, we get what's called an inversion. And if we end on anything that's planar, we only get one product. So This isn't the best set of practice problems because I really only gave you one of these on accident. But we'll talk about the other situation. The atom that this is connecting to is what's important, right? The atom that the major bond that's formed between that sulfur and that carbon, that's a planar carbon, right? It's trigonal planar. And we end on a tetrahedral. So we've gone from something that's flat to something that has dimension to it, that has three dimensions to it. So that means where this adds, it both adds as the wedge, right? It can attack the front side of this molecule, or it can potentially add as a dash to the back side of the molecule. So then I compare these two molecules. There's only one stereocenter in both of them. I would say these two molecules are enantiomers. All right, likewise, for these, I'm gonna go pretty quick through the arrow pushing thing. This one's a little funky, but it's not that bad. So I'm forming a bond with a carbon. That's a planar carbon, right? It's an sp2 carbon. There's a double bond on it, and I'm ending tetrahedral. So that means that I'm going to get two different products because I'm going from flat to not flat. And so that carbon on one part of the carbon is going to be a wedge, on one is going to be a dash. It doesn't, you could put the wedge or dash here. That would also work. Um, so just as long as something off of this carbon's opposite, right? Either way, you're making one stereocenter R and one stereocenter S, and that's really all that matters. These two things are again enantiomers of each other. I'm going from planar to tetrahedral, so I should get both the wedge and the dash forms. Because I'm adding into a flat thing. So when you add into something flat and you turn it into three dimensions, you get both. All right. So these two things, again, there's only one stereocenter. Actually, these are actually the same molecule technically. Oh no, they're not. There's a double bond. Nope, these are enantiomers. One chiral center and it's opposite. They're opposite of each other. This is kind of a trick question. So again, we're going from planar to tetrahedral. Uh, since this is the trick about this. Since this isn't a chiral center, technically these are the same molecule, so it doesn't really matter. Whether it's wedge or it's dash. Um, right, you can imagine spinning this bond around, but because this isn't a chiral center, it's connected to two methyls. They're not different molecules, they're the same molecule. That's a little bit of a trick. I doubt I'll ask that on a test. One thing that I wish I had shown more of, or a couple of different things, is one, you can form an enantiomer, right? Like, so if there was another chiral center here, these would now be enantiomers, because I have two chiral centers, one of them the same as one of them's opposites. So that's another potential, or sorry, these are diastereomers. Um, Now because they're they have multiple chiral centers that are different that are not opposite, right? So be aware that diastereomers are a possible question. So really you're looking just for another chiral center. Is there another chiral center on the molecule that matches? That would make them diastereomers. And the other thing to look out for is which I didn't show, would be something like this. And this is what I mean by inversion. It doesn't matter what it is. It's some, if I have some nucleophile and I'm replacing a chiral center, I will get an inversion and I only get one product. So this would be a stereospecific reaction. So if I'm going from something that's tetrahedral to something that's tetrahedral, then I'm going to maintain stereochemistry. I'm just going to invert it, right? I don't get multiple products. I just get the opposite product. All right. Resonance. We're not going to spend a ton of time on this, but I do want to spend a few minutes because resonance is really, if you don't understand resonance, it's going to be really hard to understand acid base and a lot of other stuff in organic chemistry. So I know it seems like a pain, but resonance is really important. So when I think about resonance, just like when I think about air pushing, I'm thinking not necessarily about bonds moving and just pushing bonds around. I'm thinking about what things want electrons and what things want to get rid of electrons, right? Getting to the heart of why things do things is really kind of gonna set you up well for organic chemistry, right? Bonds aren't just moving on their own. It's not helpful to try to just memorize how bonds move. You got to think, is there an electron donor or is there an electron acceptor in this picture? And one thing that we've learned through resonance practice and through that resonance worksheet, if this is still something you're struggling with, is an oxygen that's not part of a double bond, that's an electron donor. I might even just write that out on a test. Like, hey, that's an electron donor. I know no matter what, electrons are going to flow off of this thing and towards a double bond, probably. But this carbon can't hold another bond, so we have to push it, and we're just going to push it to the next carbon. So this is the pattern. This is the electron donor pattern. You're going to see it over and over every time you have an electron donor. It feels wrong at first, I know, to stop that charge on a carbon, but stop it once. You got an electron donor, form a double bond, push the neighboring double bond to the next atom. All right, now we have a new fresh electron donor, got a double bond next to it. So I'm just going to push it to the next atom, next bond, and then push the next bond to the next atom. That's it. That's the pattern. In essence, what we're seeing is, and you can see it pretty clearly here. All we're seeing is that this double bond and this charge are flipping positions, but because it's a negative charge, we have to push the arrows from the negative charge through the bond. So again, first thing I'm looking for, this is an electron donor. It's a nitrogen that's not part of a double bond, it's an electron donor. Period. End of story. I see a double bond next to it, so I know I can push these electrons down to that bond and through to that double bond. Don't forget your charges. And that question's pretty straightforward. All right, now I see an oxygen that's part of a double bond. So this is not an electron donor anymore. This is an electron acceptor. There's two patterns with electron acceptors. The first one is to break a carbonyl up towards itself. And then whenever I see a carbocation, whenever I see a positive charge on a carbon and a double bond next to it, I can do kind of what I was doing up there, where I'm just flipping the double bond with the charge, but the arrows are a little bit different because we're pushing electrons in the opposite direction. And then we can do it one more time because I have another double bond next to a positive charge. All right. Oh, I've got one more resonance question. So in this one, I've got an electron donor and acceptors, right? So I prefer to think about starting from the donor. So there's a lone pair on this carbon. It doesn't really matter which direction you go, they're equivalent. So if you treat this like an electron donor, you push the electron donor down to this double bond, then you kick the neighboring double bond up to the next atom. We've done this exact thing before. It's the same pattern. Resonance is one of those things that seems so much more complicated than it is. It's really just three patterns you do over and over, but the hard part is recognizing one, that is electron donor, electron acceptor, and two, keeping yourself to those patterns and not just doing whatever you want to do, right? Not just trying to move bonds around. Stay calm. There's three patterns. There's carbonyl going up. There's a double bond next to a positive charge where the double bond just goes and switches places with the positive charge. And there's the electron donor pattern where an electron-rich thing gives electrons to form a double bond, and that pushes the neighboring double bond onto the next atom. Those are three patterns. You see them over and over again. Once you do enough of these resonance questions, they should become pretty clear. Now, I have a couple of things I can do here. Probably the way that's safest for you guys would be to just redo the pattern backwards and get to that starting material again, right? You can notice if I did the electron uh, donating pathway backwards, that's what I'd get. But we want to show all possible resonance structures, and we know that at some point in time, this has to accept electrons. Electrons have to go up into that carbonyl. So we can actually push this double bond all the way up to the carbonyl and show that all in one step. So if you feel uncomfortable doing that, just do an electron. You can do the electron donor pathway up to here, and then again, you can imagine doing it from here back up to the top. Or you can do what I just showed, which is just to kind of skip a step and push it all the way back to the other oxygen. All right, that's resonance. Do you guys have any questions about resonance before I move on? How do you know when to stop? You know, yeah, you know when to stop, essentially when you start going, yeah, these are great answers. When you start going backwards, right? So like, okay, now I've got a positive charge next to a double bond, but if I were to do this, I would just be going right back to the starting material or to this other one, right? I've just gone in a loop. So it's not wrong. You just don't need to show it. You don't need to keep going. So if you find yourself repeating yourself with no like here, I was just saying to go back to the starting material, but that was because we had a clear indication that there was another place we could go. But if I'm here, but if I'm here, when I start going back up the chain with no other place to go, that's when resonance is done. Here, resonance is done, right? Because okay, yeah, I've got an electron donor. I could push it back down up into this nitrogen, but that would just get me back to the starting material. So I don't need to show all that. Like a lot of times, resonance just goes along a chain, and once you're done, at the end of the chain, it's done, right? So I know I can't keep pushing because that's an sp3 carbon. There's no double bonds to push into, and so I'm kind of done. Does that answer the question? All right, any other resonance questions? I would like to see an 80+% average on resonance questions on the test. We've been working towards it. This will be the third time we're getting a resonance question. Um, if we don't get that 80 plus, I'll just keep asking resonance questions, I guess. I don't know. Um, how can I always mistakenly turn on the eraser, but I can never purposefully turn it on? All right, we're gonna jump into acid base. All right. So whenever I'm asked more acidic, I didn't hold your hands this time. You've got to draw out the conjugate base, right? We know things are acidic because of the stability of the conjugate base. Not because it looks better, not because it has more electronegativity. That can work for you a lot of times. But if you're not thinking about forming the conjugate base, which in this case would be this, I've formed the conjugate base and I can now determine the stability of this resulting negative charge using REO. REO is only used for finding stability of the conjugate base. You can't just use REO for the acid. You have to get to the conjugate base. I'm now comparing these negative charges. This one is more stable. It's got a more stable conjugate base because of electronegativity. This is why you have to draw out the conjugate base. There's no OH here, right? There's no hydrogen to take off of this oxygen. So there's not really a acidic thing. It doesn't matter. The only hydrogen I could possibly take would be off one of these carbons. And there's no resonance, there's nothing going on with that guy, right? It's not a stable charge. So this is kind of one of the questions that we talked about on Monday, where you can't just assume that you can't say the oxygen's more electronegative, so it's more acidic. No, acids give protons. We have to know where that proton is coming from. The only proton is one of these carbons, and that's not acidic at all because the nitrogen is more electronegative than that carbon. Likewise, here it's pretty clear that the acid I'm talking about is this amide, where here it's one of these carbons. It doesn't really matter. I think technically that would be slightly more acidic. Um, but they both have resonance, right? They both can push up into this carbonyl. Things have resonance with acid base are really in general if you have an electron donor, electron acceptor next to a double bond or a carbonyl, right? That you can directly interact with it. So it's helpful to draw out the conjugate base so you can see, hey, these both have resonance, right? But the difference is the one on the left is more electronegative. That negative charge is more stabilized. I did not mean to make all of these electronegative. Um, that was not the purpose. So be prepared for something that's not electronegative on the test. Yeah, I wasn't trying to be like sneaky here and say, hey, everything's electronegativity. No, I was just kind of like forcing you guys, seeing if you guys would draw out the conjugate base, right? So the conjugate base in this situation is removing one of the protons. So we have a neutral oxygen and a neutral nitrogen. The same rules apply, right? We're still comparing these conjugate bases, and this one's going to be a little bit more stable than this one because oxygen's more electronegative than nitrogen. So you've seen this format. I don't think this is too bad. So this is kind of a different way to ask the same question. Okay, someone asked what hydrogen do you take off? You take off the most acidic hydrogen. Um, so in this case, I know that the hydrogen on this nitrogen is going to be more acidic than any carbons. But in this case, I know that um, the only hydrogens I have are on these carbons and this carbon. These hydrogens are going to be way more acidic than this one because these have resonance with the carbonyl, right? You'll have resonance if you're one away. So you always take the most acidic hydrogen you can take, right? And so generally that means you're taking one off a heteroatom because those are more electronegative. So that's a good place to start. But if I don't give you an NH or an OH, then you're gonna have to take it off a carbon. And so with carbon acidic CHs, I'm looking for two things. Either it's an H next to a double bond or an H next to a carbonyl. because these have resonance, or a hydrogen on an sp3 is less acidic than an sp2 or an sp. So looking at triple bonds is often another tell, or the hydrogens next to a double bonds and carbonyls, right? Because this is orbitals. So if there's not just a heteroatom screaming out to you, that's what I'm looking at, right? My first thought was, hey, these hydrogens are next to this carbonyl. They'd have resonance with them, so these are the ones that make the most sense to take. Does that make sense? That's a good question. It kind of ties into this question, right? We're thinking about this in a different way. How do I know which hydrogen to take? Well, we're going to take the most acidic hydrogen. So, um, there's no OH, there's no NH, there's no nothing like that on this. So, what hydrogen is the most acidic hydrogen? Well, it's got to be one on a carbon. Here, I'm going to go ahead and have this chart by us because this actually will be useful for us here. Mhm. So the only hydrogens on this molecule are CHs, right? So um, I'm looking for anything that matches this picture or this picture, right? I don't have any double or triple bonds directly connected to a hydrogen, right? So that's not going to work for me. But I do have a hydrogen that's one away from this carbonyl, right? So I have a hydrogen right there, right? So if I took this hydrogen, that negative charge would have resonance with this carbonyl. So that's my hydrogen. It's the only one that makes any sense. All right. Well, now I do have heteroatoms with hydrogens on them, right? I have a nitrogen with a heteroatom with um, hydrogens on them. If I compare this one is going to have resonance with the carbonyl. This one isn't. So that's a pretty clear indicator that's my more acidic hydrogen because of resonance. So this is resonance. This is resonance. Um, Again, I have no heteroatoms with hydrogens on them, so that's not a choice. Um, so I have to find the most acidic carbon hydrogen. Well, uh, I'll go ahead and tell you that resonance is the strongest, is a stronger force than the orbital stuff. So yes, it's not the worst idea to take a hydrogen off an sp2 carbon. It is relatively acidic, but this stabilizing force of having this hydrogen have resonance with this double bond is significantly stronger. So we almost always prefer resonance, right? So I'm looking here, right? A hydrogen next to a double bond, a hydrogen next to a carbonyl. That's when I'm talking about CHs. All right, this one's a simple electronegativity one. Oxygens, that OH is going to be more electronegative than the NH. And this last one, so this last one, I have a whole bunch of, there's no heteroatoms to look at. So I have a bunch of carbons. I have some sp3 carbons, some sp2 carbons, an sp carbon, an sp carbon. I do have a hydrogen sp carbon, which is preferable. That's more acidic than an sp2 or a sp3. So this one would be my most acidic proton because of orbitals. All right. So that kind of actually answers the question that you were just going off of, right? How do I know? Well, what's the most acidic hydrogen in that picture, right? It's usually something on a heteroatom, but if there's no hydrogen on a heteroatom, we have to look at resonance and orbitals. What would be an example of charge? We did it, there was a recitation worksheet question like that, but it's pretty easy, right? What's more acidic? Wow, no one wants to participate. The thing with a positive charge, right? This is going to be more acidic. It's going to want to give a proton more. It literally has a positive charge. The reason why is because of charge. So charge can be pretty straightforward. Right? Charge is a little bit more complicated when you think about it the opposite way, like what's more basic. Um, it's not really that much more complicated. What's basic is the opposite of what's more acidic, right? So a positively charged thing is going to be less basic because it's going to want a proton less. Does that kind of make sense? All right. I think I think I answered the which hydrogen you want to take off while talking about this. Induction again. Okay. This goes back to this is that's more acidic because if I take that hydrogen away, the negative charge is kind of stabilized by these nearby electronegative things. So that's induction. Induction would be, hey, there's negative electronegative things nearby that can kind of help stabilize the charge from afar. It's a less common thing and it's pretty obvious when you see it, just like charge. Are we good with acids? Make sure you draw the conjugate base. Make sure you can locate a hydrogen that is acidic before you move on. Don't just say oxygen is acidic. No, it's got to be an oxygen. Like this nitrogen is not acidic because there's no hydrogen on it. So it cannot be our most acidic hydrogen. More basic is the opposite. This is more basic because of electronegativity. That negative charge is less stable on a carbon than it is on a nitrogen. Uh, Carbons don't want a negative charge. They are more electropositive. They're further on the left on the periodic table. But you can't, this is one of those situations where you can't just say, oh, carbons are always more basic. Negatively charged carbons are, but look, this carbon already has four bonds. It cannot take another bond, right? This nitrogen has a lone pair, it can take another bond. That's fine. But this literally cannot take, it cannot act as a base. It cannot take another proton. It's impossible. It would make a carbon with five bonds. So this is the only option out of default, right? There's not really a reasoning here. There's not really an answer you can put here for this. I was just more trying to catch you guys thinking about this. Um, Again, I didn't mean to go back to electronegativity so much. Uh, Nitrogen has a less stable lone pair than oxygen, so nitrogen is going to be more likely to take to be a to be a base, to want to take a proton, right? Nitrogen would be happier with a positive charge. So nitrogen's always going to be more basic than oxygen. I would say it's not helpful to draw the conjugate acid for bases because REO, the thing we know how to use to compare things, is uses the conjugate base. We just always compare bases to each other. So whether if I give you the base, compare bases, follow REO. If I give you the acid, create the conjugate base so then you can compare it. That'd be the best way to do it. So REO is really best used to compare conjugate bases. All right, which direction is more favored in equilibrium? So with these questions, I look to char
Oh,
with these questions, I always look to charge. What's the more stable charge, right? Someone says, when will you compare the acids, the given acids to each other? We already did that. That's what's up here. And in those cases, we do the conjugate base so we can compare conjugate bases. An acid has a more stable conjugate base. A more stable base is a worse base.
For
So,
these ones, sorry.
yeah.
For these ones, like sometimes it's really obvious like what to compare, but like how what's a good way to like know which ones you're looking at and comparing the charge on?
Well, there's only so many things with a charge, right? So,
Mhm.
and this one, the charge is hidden. This goes
Yeah.
back to what I was saying earlier. Anytime you see a metal, potassium's one of them, I want to draw out the charge.
Hmm.
It helps me see things. It helps me compare things. It helps me really understand the true nature of these, right? So in this picture, really, I'm just looking at the charge, right? I've got a charge on a oxygen and I've got a charge on a chlorine. What's more stable?
The chlorine.
The chlorine. Done, right? What I'm doing is I'm comparing the conjugate bases, right? These are the conjugate bases, and I'm saying this is the more stable conjugate base. Um, that's what's happening when I do that. Um, but I think it's easier just to think about charge.
Okay, thank you.
Yeah. Like here, this is charged and this is charged. There's a charge, there's always, if there's a charge thing on one side, there's gonna be one charge thing on the other side, right? There's a balance of charge. So this thing's charged, this thing's charged. What's more stable? What's happier with the positive charge?
The nitrogen.
The nitrogen. Nitrogen's happier with a positive charge for the same reason that oxygen's happier with a negative charge, right? It's an electronegativity question.
Okay.
All right. Now this one's kind of tricky, right? You have to say, what's the difference between these nitrogens? What's really the difference?
Resonance?
Kind of. There is resonance here that's not there, but I mean, yes, but there's a bigger thing here. I guess not bigger, but a different the same idea, right? This That's an sp2 nitrogen and that's an sp3 nitrogen, right? Um, so we have to compare an sp2 nitrogen to an sp3 nitrogen. What do we remember about sp2 and sp3 in terms of acidity? sp2 is more acidic, right? Or sp2 makes the more stable conjugate base. So those
Hmm.
are the two different ways you can think about this, right? So this is more acidic, which means I'm going to favor the other side. Or you can say this conjugate base, right? So this is the acid, and this is its conjugate base after you remove the proton. This is an acid. This is its conjugate base. This conjugate base is more stable because it's sp2. So the side with the more stable base, or the side away from the stronger acid, is the more stable side.
What?
That's a good question. So let's do a different one. Let's do a different example, but let's use a negative charge. All right, so So Simon said the side away from the stronger acid is the more stable side. Yes. Okay. What's the more stable side here? This might be clearer. What's the more stable conjugate base? What negative charge is more stable? The right. Why is this more stable? Because that conjugate base, the negative charge is sp2 hybridized. That conjugate base is on an sp2 carbon, right? The negative charge is on an sp2 carbon.
So is it like more important to look for the negative charge, like the base, the conjugate base?
Um, yes.
Okay.
Sometimes a positive charge is easy, right? Sometimes this is super easy, right? It's easy for me to compare nitrogen to an oxygen, right? But I can think about this in the same way. This is more basic than this, and so I'm going to favor the less basic side. Or this is more acidic, right? If it helps to, this is more acidic than this is, so therefore it's going to favor the other side. Or you can think of it like this is a more stable conjugate base than this is because it's more electronegative, so it's going to favor the conjugate base side. All of these things are connected. So however, whatever works for you. So in this case, the conjugate base, okay, let's simplify it. Look at the conjugate base. All right. Look at the negatively charged thing. Look at the thing that's most negative and follow REO.
Okay. Thank you.
So here, this is more negative than the positive thing, right? So that makes this the conjugate base. This is neutral, which means it's more negative than the thing on the other side of it. So that's the conjugate base for the. Does that make sense? Does this help? I don't know.
Yes.
So these are the conjugate bases. They're the most negative thing on either side of the picture. And so if I follow REO, this is more stable conjugate base because it's electronegative.
Could you use that like same logic for the one we were just doing the like
Yep, let's do it here, and then I'll do it the one below it.
thank you.
This is the most negative thing, so this is the conjugate base. This is the most negative thing, so it's the conjugate base, right? This ne conjugate base is more stable because it's sp2 hybridized. So sp2 is more stable conjugate base than sp3. Does that make sense?
Yes, so that one would be favored.
So here, the most negative thing on this side of the equation is this. So this is my conjugate base, right? So that's my acid, my conjugate acid, my conjugate base. The conjugate base for this guy is over here. And so this conjugate base is more stable because it's sp2 hybridized. This is less stable because it's sp3 hybridized. This also has resonance, which helps stabilize it, right? It's actually one of the main reasons why hybridization is more stable.
Okay, that makes a lot more sense. Thank you.
Cool.
I'm
But
confused.
yeah.
For the one before this, like on the other page, yeah, like that one, I always look at the conjugate bases and then like the O would be more electronegative, but then the end is sp2. So how do you like figure out which one is more stable from the bases for that one?
Uh, electronegativity is going to play a bigger role than hybridization.
Okay, that makes sense.
Hybridization plays a pretty small role. Which is why this question's hard, right? Hybridization is actually a pretty small difference, but it is a difference. All right, so what's the most negative thing here on either side of these equations? This is my conjugate base for this side. This is the conjugate base for this side, right? So I'm comparing these two things to each other. Um, this one's more stable because, again, it's a negative charge next to a double bond, where this is a negative charge not next to a double bond. So there's resonance here. That's more favored. It's a more stable conjugate base.
I have
So,
a quick question.
yes.
So, when using Ario, how should we be able to know which is more powerful? Like you said, electronegativity is more plays a bigger role than hybridization. So, how do we know that? Like, is there a ranking system on which is more powerful?
Mm, no, that's what PK is for. In general, I'll try not to give you ones that are directly contradictory. Um, but like in general, electronegativity and resonance are king, you know?
Okay, yeah, that makes sense. Thank you.
Like the other ones matter, but like, okay, so this is induction, right? I think it makes logical sense that like having the thing that has the charge being more electronegative matters more than having some electronegative things a couple bonds away, right? So it like makes sense that electronegativity makes a bigger impact than induction. Um, charge probably makes the biggest impact, charge is big. Like something literally positively charged is going to be more acidic. But no, I won't make you rank them. I mean, that's why I kind of limit myself to these questions because it forces there's only one difference, right? I'm trying to make it clear. I'm trying to gauge that you understand the difference. I'm not trying to make you in general determine kind of small differences. This one I felt like I could get away with because it's a nitrogen with a positive charge. It's gonna be significantly more basic than that oxygen, even though it's sp2 hybridized. Actually, yeah. That's a good question though. I'm gonna try to keep that from being a major thing.
Okay, thank you so much.
Yeah. All right, now we're on to the last thing. Are you guys okay with acid base? Do you want to spend another minute here? I've got about 30 more minutes. All right, well then let's jump into nucleophile electrophile. All right, so nucleophiles are negatively charged things, usually amines, alcohols, sometimes double bonds, but I wouldn't bank on it. Electrophiles, carbocations, things with leaving groups. So those tend to be your halogens. And then carbonyls. So I'm looking for something from each side of the chart. It might even be useful to draw these charts out at the beginning of your test. I see that looks like a nucleophile. The carbon attached to the leaving group, remember it's always that carbon. That makes sense to be my electrophile. I don't have any acid or base. So step one is acid protonates electrophile or base deprotonates nucleophile. Step two is nucleophile attack electrophile. I'd have those in mind when I do this. So you can see that it looks like a base has already deprotonated this, right? There's a negative charge here That probably came from a base. So that step has already been accomplished. So we can just jump straight to nucleophile attack electrophile. And I get that. Again, this is where being able to push arrows effectively is really helpful.
I have a question.
Yes.
Why didn't we add an additional bond to the oxygen?
What do you mean?
Like it's okay, like for example, I count one,
Uh,
2, 3, 4, 5 carbon. Okay.
yeah, it should be 1, 2. I numbered this backwards, but whatever.
Okay, thank you. Because I was confused
Yeah,
for a
sorry.
second.
I must have just missed that. Yeah. See, I do it too. Always number your carbons. So I'd lose points there on a test. So be better than that. Um, all right. Again, this is a very similar question, but it's trying to show you like, hey, we're doing the same thing, right? It's the same reaction, but now, mm, I'll go ahead and number the oxygen because it's going to be part of the ring. Nucleophile, attack electrophile, kick off leaving group. All right. So since oxygen, which I gave number 1, is connecting to carbon 6, that's the chain, right? The chain is 6 big between. So okay. Someone just asked how to number. Numbering's yours. Number however you feel like helps you, right? There's no right or wrong way to number. I'm not going to grade you on numbering, but you number in a way that's helpful, right? For me, I just numbered this one. I just numbered the carbons here so I could make sure I didn't lose any carbons because I wasn't worried about anything else. But on this one, I'm saying, okay, well, I know that this oxygen's attacking the same chain it's on, so I'm going to form a ring, and I want to know exactly how big that ring is. So if my oxygen is connecting to that carbon, right? If one is connecting to 6, that means I have a ring that is 6 members big. And this is 1 and it bound to 6 and 5, 4, 3, 2. And there's nothing else on this chain, so I don't have to fill anything else out. So the numbering is just something that's helpful to you. I'm not going to grade you on it, but it's really helpful to make sure you don't drop carbons, or in this case, to make sure you know exactly how big your ring is going to be. So anytime something attacks itself, attacks the same chain that it's on, it's going to form a ring. All right. So here, this is my nucleophile. This is my electrophile, the carbon attached to the carbonyl. So I have what best describes me? I have a nucleophile attacking the electrophile because I don't have an acid or a base. And I have to, because this carbon has 4 bonds, I have to break a bond. So I'm going to break that carbonyl. Should be getting pretty used to doing that to a carbonyl by now. And now I've got 1, 2, 3, 4, 5, 6. So I've got a chain that's 6 big. One of those is the oxygen. One is bound to 6, 5, 4, 3, 2. And then 6, that oxygen gained electrons like that. If I drew the oxygen on the opposite side of the hexagon, would that be marked wrong? No, I mean, if I flipped this around like that, it would be the same molecule. How do you know whether it becomes part of the ring or becomes branched off the ring? So, 1 is connected to 6. So everything that's between 1 and 6, so everything that connects 1 to 6 directly is part of the ring, right? This is the circle you make, right? Like if this is my right hand and this is my ankle, and I grab my ankle, what's part of the ring is everything between my right hand and my ankle. If my left arm was hanging off over here, that's not part of the chain. That would come off at 3, right? Because it's not directly connecting my hand to my ankle. And we'll see that more in these next practice problems. Right? This oxygen is outside of the ring because this oxygen connected to 6. And so this oxygen would not be part of that chain between these two things that are connecting to each other. Oxygen, that's my nucleophile. We'll see more practice. Electrophile. I don't have an acid or base, so nucleophile, attack electrophile, kick up. 1, 2, 3, 4, 5. So now my ring is only 5 big. I have an oxygen in it because 1 is an oxygen, and it bound to 5, 4, 3, 2. There's a hydrogen on 1, and on 5 is an OH. That's gained electrons from this double bond. Someone said, if we left the O minus where carbon 1 was in the last picture, would it still count as the same structure? So there is, based off how I numbered it, there is no carbon 1. There's an oxygen 1 and a carbon 6. Are you asking like if I had done this? That would be wrong. Because this oxygen needs to stay connected to carbon 6. Is that what you're asking? I don't know, you're gonna have to speak up because I'm not quite sure what you're asking. I want to make sure that you understand so you don't get it wrong on the test. So I don't see anything else on this chain, so I'm done here. So here I've got a nucleophile, it's an amine now, and I've got a leaving group. I've got no acid or base, nucleophile, attack electrophile, kick off. 1, 2, 3, 4, 5, 6. So the nitrogen 1 is connecting to carbon 6. So I've got a 6-membered ring with a nitrogen in it. Where this is 1 and it's connected to 6. That nitrogen still has 2 hydrogens on it and a positive charge. There's nothing else on the ring. All right, so now we've added a little bit of a twist. NaH. This is a strong base. It's tempting to think this is an acid because there's a hydrogen here. But what's more important is this. That's a metal. So whenever I have a metal, I'm going to draw out the ionic bond. So sodium has a positive charge, hydrogen has a negative charge. Would it help to memorize all the strong bases and acids? I would recognize the chart of bases that I put up in this unit, in this chapter, or on this lecture note. I talked about non-nucleophilic bases. We're going to talk about them more. But really, I would know the bases I would know right now would be sodium hydride and like KOTBU or NaOTBU, right? These are bases, right? One of the dead giveaways is this metal. Each one of them has a metal at the front of it. So it's actually pretty easy to recognize acids and bases in organic. Acids tend to start with hydrogen, where bases tend to start with a metal. So this hydrogen has a lone pair, right? It's negatively charged. So step one, now that I've got a base present, is base deprotonates nucleophile. So the nucleophile is my OH, so I'm going to take the proton from it. And look, what's happened is now I've just gone back here, right? I'm now at this point. I'm now here. One thing that I want to tell you guys, I want to be clear about this. You have to show these as two separate steps. You can't show the base deprotonating and the nucleophile attacking in the same step. These are two separate steps and they need to be shown as two separate steps. You will lose credit if you show these all at the same step. This six-membered ring with an oxygen in it. And there's nothing else coming off of it. So that's it. This is an acid, right? It starts with an H, a sulfuric acid. Also, a strong base, like you learned in general chemistry, is not a strong base in organic chemistry. Like it's a kind of a different idea. You can't like you couldn't memorize all the strong bases if you wanted to in organic. It's more helpful to recognize structure, right? We know that negatively charged things tend to be more basic. We know that bulky things tend to be basic instead of nucleophilic. What? Okay. Someone asked where the hydrogens went to make the oxygen negative. So I had a hydride and it took a hydrogen off of that OH and gave the bond to the oxygen. That'd probably be that's the more accurate way to draw this. And so that leaves me with H2 and a negatively charged oxygen. So that's what happens.
I have a question. So like when we're done with our ring, we should have like to the side Br with a negative charge, Na with a positive charge, and then just H2.
Yeah, I mean, I really just care that you show the things with carbon on them, but if we wanted to fully balance this, then yes.
I think it's best for me to do that, or else I'll put the charges on the ring.
Okay, we don't put the charges on the ring.
I
But
won't.
but at a certain yes, okay. If this is helpful, that's great. But at a certain point, we need to be able to evaluate a structure for its own sake, right? Like, all right, yes, there's a negative charge in this picture, but that doesn't mean we need to force a negative charge here if everything looks right, right? We recognize that this bromine left and has a negative charge. The thing is that we're going to get into inorganic chemistry, you're going to get into places where you do 5, 6, 7, 8 steps. And to have to draw all of these out for each step would start to become a real big hassle. So, one of the goals would be to get used to just being like, all right, this oxygen has two bonds on it. So I know that it's neutral. Done. Like this carbon gained electrons, this carbon lost electrons, so it's neutral. Like everything in this picture is going to be neutral. But right now, if that's helpful for you to balance all of it out, then yes, this is it. I'd rather you do that than get it wrong right now. You're still learning, you're still getting used to these things. All right, so I realize I just did this. So we have an acid. So step one is for the acid to protonate the electrophile. It gives a positive charge to that oxygen. Then step 2 is nucleophile attack electrophile. I've got a 1, 2, 3, 4, 5, 6 membered ring with a nitrogen in it that has a positive charge and an OH. If it helps, HSO4 minus is still sitting around, which is what happens when you took a hydrogen from H2SO4. So that's why that's the balanced equation. So I've got a metal. I'm going to go ahead and draw out the ionic bond. First thing I do, someone said, why does the oxygen receive the hydrogen when the electrophile is the carbon? This carbon doesn't have lone pairs to take a hydrogen with. There's nowhere to put it, so we put it on the oxygen. It's always going to be the case with carbonyls that this oxygen takes a proton, then you attack the carbon. Um, you kind of get used to that pattern, but yes, it takes it because this has lone pairs to take the hydrogen with. All right, we've got 3 more questions. All right, this is a base. Step 1, base deprotonates nucleophile. I've got a nucleophile, I've got an electrophile. I'm going to shorthand benzene to be phenyl. Save me some time. Step 2 is nucleophile attack electrophile. And this gets back to when someone was asking, how do I know when something's inside of the ring or outside of the ring? So this is a good question to gauge that, right? So I know that nitrogen 1 attacked carbon 5. So I've got a 5-membered ring. I'm going to start with my 5-membered ring with a nitrogen inside of it. That's 1. It bound to 5, 4, 3, 2. So this is the heart of everything, right? Every atom I've got bound is part of the ring. Then on carbon 5, I have an oxygen that gained electrons. On carbon 5, I also have this methyl. So there's a methyl here. On carbon 4, I have 2 methyls. And on my nitrogen, I have a phenyl coming off of it. So still connected to that nitrogen would be the phenyl. Does that make sense? We still make the core, we still make the ring, and then we number it and make sure all the numbers are in the right place. All right. I see a metal. I'm going to draw out the ionic bond first thing. And that's a base. Bases have metal in them, right? Puts a negative charge on something that makes it basic. So I've got a base. I've got a nucleophile. I've got an electrophile, right? A carbon attached to a leaving group. Someone asked, does it matter how we draw the ring? Nope. As long as we can tell pretty quickly if it's the right ring or not. If it's rotated, like, that's still the right answer. Good question. All right, that's a base. Step 1 is base deprotonates nucleophile. Take the proton from the nucleophile. Step 2 is nucleophile attack electrophile. And that should be my final product. You don't need to draw the chlorine, but if it helps you, there's the chlorine. And the OTBU and the potassium. Right? That's everything that's in the equation. You don't need to draw those, but if that helps you balance the equation, that's it. I will say, notice something. We started with a negative charge on an oxygen. We ended with a negative charge on a chlorine. So we've this is way more stable than the starting material. All right. We're still kind of doing equilibrium here. We're just not really thinking about it as much. We've created a more stable charged final product than we had at the beginning. All right. So I know this is a nucleophile. No questions about it. But then I see something like this. Well, this looks kind of nucleophilic, but this looks kind of electrophilic. So this is called a carboxylic acid. It's kind of funny because it can do either. It can be nucleophilic or electrophilic. But in this case, my best guess is that it's going to act as a electrophile because I already have a nucleophile, right? It wouldn't make sense to have two electron donors. Jason said the only times where the charges, lack of charges, should balance on both sides and when it's resonance arrows or equilibrium arrows. The charge is always balanced. We just don't always show everything that's in there because otherwise in this step I'd have to draw this again, like I'd have to draw this again in this step, which just is a waste of time. You end up being able to kind of balance it on your own and just instead of being a slave to balancing charges all the time, understanding that it's a negative oxygen. It gave away electrons. It should be neutral in the next picture, right? I should understand that oxygens with two bonds are going to be neutral. I should be able to evaluate each picture on its own merit without freaking out about arrows. With resonance or equilibrium, because you're showing everything in those equations, there should always be a balance of charges. We just don't always show it. With resonance in particular, if your charges are not balanced, then something's gone wrong because you only ever have one molecule in resonance. So it's not like there's going to be another molecule you're just not drawing. So I would say the balance of charge is important. It's important to know that, but there's going to be a lot of times going forward. This is going to look more like what we do going forward than pretty much anything else. So um, understanding that being able to push arrows and understand what charges should be just based off of that is more important than I think always being worried about the balance of charges. The charges are balanced. Like I'm not usually thinking about balancing out charges all the time when I'm drawing mechanisms and arrow pushing because if you follow the rules, the charges will be balanced instead of the other way around. All right. So step one is electrophile. Takes acid. Acid protonates electrophile. Step two, nucleophile, attack electrophile. Actually, I'm going to redraw this. Cool. So those are the same steps. All right. We've gone through every one of these, every question on here. Where do you guys think you're struggling the most? my guess would be discomfort about equilibrium arrows, maybe, or resonance. Those are probably going to be the two. If I already guessed, those are probably going to be the two lowest scoring on averages. Maybe something in here. But yeah, it feels like which side is favorable. So hopefully it made sense to just to simplify it in the way that we did it, right? So find the conjugate base. So that's going to be the least charged version of the molecule. I guess least, lowest. Nope. How about most negative? So step one, find conjugate base, which is going to be the most negative version of the molecule on either side, and then REO. So here, that's more negative. That's the most negative. This is more stable, so therefore it's that side. This is neutral, and that's positive, so this is the more negative, so that's the conjugate base. That's neutral, or that's positive, that's neutral, that's the more negative side, so I'm comparing this conjugate base to this one. This one is the more stable conjugate base because it's negative, because it's electronegative. Um, Someone said do all the steps. I can't really do all the steps. I mean, here's the steps for this, right? So planar to tetrahedral, you get a wedge and dash. Tetrahedral to tetrahedral, you get an inversion. And on a planar, you only get one product. Arrow pushing is arrow pushing. In general, negative goes to positive. That's what I'd be looking for. Um, Resonance. The key here is find electron donors and acceptors. That's where it starts. That's where everything begins. And then there's the three patterns. If you don't know what those are, go to that worksheet I posted. If you have anything less than a perfect score on the last quiz with resonance, you need to do that worksheet. It points you to donors, acceptors. That's the most important thing with resonance. If you sit down in office hours with me and ask me a resonance question, and I say, "Where's the donor or acceptor?" and you don't know, then I'm going to tell you to do the worksheet, and then come back to me when you understand what a donor and acceptor is. At the end of the day, that's what you need to be able to do. Acid base. So with acidic, so acid, turn it turn into conjugate base, areo with base. It's already in the base, so you can just do the areo straight up. More stable, more stable conjugate base, more acidic, m- more stable regular base equals less basic. So that's that. This is a big one. being able to recognize carbons, which carbons are more acidic based off of nearby resonance or its hybridization. It's a good one to keep in mind. We just did this, and then, yeah, here's your chart for that. So there's your quick instructions for every one of those steps. I hope that was helpful. I've got to go to a meeting. I'll get these up hopefully in the next little bit. But yeah, those are your steps for everything. That's the thought process I go through. Um, I hope to see you guys in office hours today. I might be a little bit late because I've got this meeting from 10:30 to 11. But good luck on the test tomorrow. Um, good luck on the test tomorrow, and I will see you then.